In this video, we're going to talk about the properties of substituted alkanes. And it's important to know because oftentimes if you understand the properties, then you can understand the reactivity of certain compounds. So the first thing that we're going to take a look at is polarity. And when we look at all of the various types of substituted alkanes, we see that most of them are polar. And if we focus our attention on the alkyl halides, we see halogens certainly have electronegative atoms attached to the alkyl group, and this creates a dipole moment. Therefore, you have this carbon-halogen bond. The dipole is directed toward the halogen, and it creates a dipole moment. And when you have a molecule that has a dipole moment, then you have dipole-dipole interactions. And we can see that throughout kind of a sequence of alkyl halides, starting with methyl fluoride. We see that methyl fluoride has a dipole, an overall dipole of 1.85 dBi. Now when we move to methyl chloride, the chlorine is less electronegative, but the bond is longer, and because of that we have an actual increase in the dipole moment of 1.87 dBi. Because dipole moment has to do with electronegativity, it also has to do with bond length. So it's important to understand the little variation in dipole moments between the various alkyl halides. But as we might expect, when you go to larger halides and less electronegative halides, the dipole moment decreases, and so methyl bromide has a dipole of 1.81 dBi, and finally methyl iodide has a dipole of 1.62 dBi. So in general, all alkyl halides are relatively polar and have about, a general polarity that is kind of consistent with one another. Now, when you take a look at alcohols, alcohols like water can engage in hydrogen bonding. And because of this, they become much more polar than alkyl halides. So the reason for this is here I have two alcohols. They can interact. The pair of electrons, the non-bonding pair of electrons on one oxygen can form a hydrogen bond with a hydrogen of another molecule. This leads to relatively high boiling points, similar to that of water, although not quite as extensive because water has two hydrogens that can form hydrogen bonds. But we can see that if you look at methanol, methanol has a boiling point of 65 degrees. Now, comparing that to something like methane, if you remember, methane has a boiling point that's very low, of minus 164 degrees. So methane doesn't have hydrogen bonding capabilities, and therefore it only has weak van der Waals interactions, and it's easy to break those intermolecular interactions. Methanol, on the other hand, you have to add more energy to break that intermolecular bond, and therefore it has a higher boiling point. We also see that with ethanol as well. Now, ethanol weighs more than methanol. We would expect it to have a little bit higher boiling point, and it certainly does, of 78 degrees. So ethanol has a boiling point even closer to that of water, and when we compare that to ethane, we see that big difference in the boiling points between alcohols and alkanes. Our next substituted alkane is an amine, and amines, like alcohols, can form hydrogen bonding. So if I look at methylamine, it has a boiling point of minus 6.3 degrees. Now you might say, wait a second, I just saw methanol has a boiling point of 65 degrees. Why is this so much lower? Well, again, you have to compare it to something that has about the same molecular weight, so we can compare it to ethane. Ethane has a boiling point of minus 89 degrees. So again, we see, it's much higher than that of ethane, and the reason for that is hydrogen bonding. Now, it's not as dramatic. And why is it not as dramatic as alcohols? Well, that's because there isn't much of an electronegativity difference, right? The oxygen is more electronegative than nitrogen, and therefore we don't see as drastic of an effect in terms of the hydrogen bonding. Now, one thing to note is that if I go from methylamine to dimethylamine, the boiling point increases because I'm increasing molar mass. But when I go to triethylamine, the boiling point actually decreases slightly. So there's two factors going on here. Obviously, I'm increasing the molar mass, but at the same time, I'm decreasing the amount of hydrogen bonding. And as a matter of fact, triethylamine has no hydrogen bonding, and therefore it has a lower boiling point than that of dimethylamine or methylamine. Well, methylamine still has a lower boiling point, but it also has a much lower molar mass. All right, so the last functional group that we'll talk about is ethers, and really only small ethers are polar. I mean, I said that all substituted alkanes are polar, and certainly it depends on the size of the R group. The larger the R group, the more hydrocarbon character you take on, and so it becomes less and less polar. That holds true for all substituted alkanes. So alcohols are polar, but if the R group is very large, it can behave as a very nonpolar entity. As a matter of fact, octanol is only very slightly soluble in water. But ethers, if we compare the structure of ethers to that of alcohol, so here's the structure of a generic alcohol, and here's structure of an ether, and we see, the big difference between the two is that alcohol has hydrogen bonding capabilities, whereas ethers have no hydrogen bonding capabilities. So there's certainly a dipole that ethers have, and when the R groups are small, that dipole is larger, and therefore they become polar. So diethyl ether is somewhat soluble in water, but it's not very soluble in water. It's not miscible with water like ethanol is. And so you see the slight or the big difference between something like ethanol and that of diethyl ether in their solubilities. The next property I would like to discuss is acidity and basicity. So this is a very important concept to understand because when we go on into the next chapter, we really need to focus on understanding, what makes an acid, what makes a base, what makes a nucleophile, what makes an electrophile. So we're going to start off with alcohols because alkyl halides are not acidic or basic. So first and foremost, understand that alkyl halides are not acidic, they are not basic to a large extent. But alcohols, like water, can behave as both an acid and a base. We could think of it as a Bronsted acid, which donates a proton, or a Lewis acid, which accepts electrons. Either way, and this is an important concept to understand, the difference between Bronsted acid and Lewis acid. But for the most part, there's not much of a difference other than our mindset of Bronsted acids accept electrons. Lewis acids accept electrons, Lewis bases donate electrons. So here's an example of I have an alcohol. It's going to react with some generic acid. The alcohol acts as a base here, right? And of course it's going to then react with an acid. And how does this happen? We donate a pair of non-bonding electrons to that proton, breaking that bond, right? We're donating to the sigma star orbital of that HB, whatever acid it is. And the result is that I now protonate my alcohol, and now the oxygen has only one pair of electrons and a positive charge. And then, of course, I get my conjugate base of the acid. Now, when you protonate an alcohol, you get what's called the oxonium ion. We've already seen this before, right? The oxonium ion. And it's important to understand the acidity, the acidic nature of the oxonium ion. And the reason for this is because we have to understand what kind of acids can protonate alcohols. Why? Well, we have to look at the pKa differences. And we see that only strong acids can protonate alcohols. The reason for this is because the conjugate acid, the oxonium ion, has a pKa of -2. So it's actually a very strong acid, the oxonium ion is. And in order to protonate an alcohol as a base to form the oxonium ion, we have to use a fairly strong base, or a fairly strong acid, excuse me. What acids can do that? Well, hydroiodic acid can certainly do that. It has a pK of -10, as can hydrobromic acid with a pK of -9. Hydrochloric acid can do so with a pK of -8, and sulfuric acid can do so with a pK of -3. How do I know that? Well, remember, the equilibrium is going to lie toward the acid that has the highest pKa. The equilibrium is always going to lie toward the acid with the highest pKa. So with the oxonium ion with a pKa of -2 is greater than a pKa of, let's say, sulfuric acid with a pKa of -3. And therefore the equilibrium is going to be favored toward the formation of the oxonium ion. So that's important to understand. You know, when we look at pKa tables, we have to recognize that that acids with a lower pKa are going to react to form acids with a higher pKa. Now, we've seen that alcohols can act as a base and be protonated, but alcohols can also react as an acid. And so if I take an alcohol and react it with a base now, what do I get? Well, the base can remove that proton off of the alcohol. And I get now what's called an alkoxide ion, RO minus. And of course I get the conjugate acid of my base, right, whatever that base is. Now, again, it's important to understand, you know, how basic or how acidic, excuse me, are alcohols. Well, if you look at table 6.8 in your textbook, you see that they're comparable, their acidity is comparable to that of water. Water has a pKa of 15.7. Methanol has a pKa of 15.5, so it's about the same acidity as water. Ethanol has a pKa of 15.9, so around 16. And then as you see, as you increase the size of the R group, the acidity decreases. So that's kind of an interesting trend, and what's actually happening there? Well, it appears that adding alkyl groups to the alcohol, going from a primary to a secondary to a tertiary, actually decreases the acidity. One of the questions is, well, why does this happen? And for many years, it was believed that it was due to the alkyl group's ability to donate electron density, right? So this is a kind of an important thing to think about. We look at a behavior and then we think about why does that behavior exist, right? So let's take a look at, you know, the structure of an alcohol. So some generic alcohol, it has a methyl group. Well, that methyl group we think of as donating electron density, right? When we talk about the stability of carbocations, alkyl groups donate electron density to the carbocation. So an alkyl group, a methyl group, can donate electron density. And what happens when that alcohol behaves as an acid? Well, it reacts with a base, right? We remove that proton, and the electrons are going to the oxygen. So the result is that I now have a negative charge on the oxygen. If the methyl group is donating electron density to the carbon attached to that oxygen, what do I have? Well, I have these a partial negative charge on the carbon connected to an oxygen that has a formal negative charge. And that's certainly going to destabilize that whole setup, right? Because of the um, uh, based on that dipole of that carbon-carbon bond. And that's how it was explained for many years. It wasn't until 1970 that it was discovered that the order of acidity is actually reversed in the gas phase. When there's no, so what's the difference between the gas phase and in solution? Well, the big difference is the solvent. And so this led us to understand the idea of solvation effects, right? Solvation effects. How easily the solvent can stabilize the organic ion that results. And we're going to kind of see this trend throughout, this idea that solvents play a critical role in stabilizing reactants, stabilizing products, stabilizing intermediates even, right? So let's try to understand this then. Here I have methanol and excuse me, not methanol, methoxide, right? The conjugate base of methanol, which we call methoxide. And I add methoxide to a solvent. Obviously, it's going to have to be a polar solvent because now I have this negative charge, so it's a very polar molecule. And so now that solvent is going to solvate the methoxide. So the solvent surrounds the methoxide. Now, when I go to something like tert butoxide, right? So now I have three methyl groups off of that carbon, and this becomes tert butoxide. Well, now the methyl groups are nonpolar, and therefore the solvation effect isn't as great, right? In other words, tert butoxide is more difficult to solvate. Now, because of that, that means that the solvent can't stabilize the anion as well as it can stabilize methoxide anion, and therefore, because because it can't be stabilized as great as that of the methoxide, then it becomes its conjugate acid becomes a weaker acid, right? Remember, the strength of an acid relies on its conjugate base. The more stable a conjugate base, the more acidic that substance can be. So if we decrease the stability of the conjugate base, we're decreasing the reactivity, the acidity of that acid. So tert-butanol is not as acidic as methanol because of the solvation effect. And what happens is in the gas phase, the alkyl groups actually stabilize the negative charge by allowing electron delocalization into the empty sigma star orbital of that carbon-carbon bond. So before we were talking about, that carbon-carbon bond donating electron density. Well, actually in the gas phase, it's the opposite effect. It's the opposite effect, right? In the gas phase, there are no solvents present, so solvents aren't even around to stabilize or destabilize for that matter. So what do we have? Well, now we have a scenario where electrons are being withdrawn somehow. They're being accepted into that carbon-carbon bond somehow. Well, what is empty? Obviously, the sigma bond is a full um, occupied orbital, right? Well, if we take a look at the sigma star bond, right, the oxygen obviously has a pair of electrons in a non-bonding orbital, and if overlap is right between the sigma star bond, the empty antibonding orbital of a carbon-carbon bond, then you can get donation of electron density. And remember, whenever we get delocalization of electrons, we get stabilization. And it's a belief that that is what is happening in the gas phase. And we don't see that in solution because of the stabilization of from the solvents, right? So, things are a little bit more complicated when we dive in to really try to understand properties of molecules. But once we do, the more we understand it, the more we can predict how they're going to interact with other things around them. Right? Now, amines are mainly Bronsted bases, right? In other words, they accept protons. And most of the time, this is the kind of the natural behavior of amines. They are bases. They tend to not be very acidic. We'll take a look at their acidic nature in a little bit, but for the most part, they are thought of as a base. Why? Because they have a lone pair of electron on the nitrogen that can donate and remove a proton. Right. So here I have methylamine. It reacts with hydrochloric acid. The amine is the base, hydrochloric acid is the acid, and we can undergo a proton transfer, where that fully occupied, non-bonding molecular orbital on nitrogen donates its electrons to the sigma star antibonding orbital of HCl, and the electrons on that bond then go to the chlorine to make chloride. So we end up getting a salt plus the chloride anion, and that salt, that CH3NH3 plus, is called an ammonium ion, right? Which we talked about naming ammonium ions. So we end up, we essentially take an amine, we protonate it, and we get an ammonium ion. Now, in the gas phase, the order of basicity follows this, that ammonia is less basic than a primary amine, which is less basic than a secondary amine, which is less basic than a tertiary amine. Why? Well, the more electron density is placed on the nitrogen, the more available those electrons are for donation. So the basicity increases. Another way of looking at it is thinking about the conjugate acid. The conjugate acid results in a positive charge on the nitrogen. So when there are groups that can donate electron density to that nitrogen, and basically minimize that formal positive charge, it's going to be more stable, right? So, our general thought is that alkyl groups donate electron density. Even though we talked about, we just got through saying, well, alkyl groups donate or don't donate electron density. Well, they still do, but there's other factors involved, right? So, in general, as you add R groups, right, they donate electron density and they stabilize the resulting ammonium cation. So the more stable you can make the conjugate acid, the more reactive is its base. Very important concepts to understand there. The more stable you make a product, the more reactive the reactant is. Okay? So, in solution, so now notice I said in the gas phase, the basicity follows this trend, but in solution the story is a little bit skewed from the reality of the gas phase. And here's table 6.9. you see that, um, okay, so let's understand what this table is saying. Uh, what you're doing here is you're comparing ammonia to ammonium. So we're looking at the pKa of the ammonium ion, and we're comparing it to the pKa of other ammonium salts, right? So if I add a methyl group, the conjugate acid is the methyl ammonium ion, and its acidity is lower, right? If its acidity is lower, that means it's more stable. It's not as willing to give up a proton. So that means it's more stable, which means that the base is a stronger base. And of course, we saw in the gas phase that ammonia is less basic than methylamine, and that trend follows. Now, I go to dimethylamine, and we see that its pKa increases of the conjugate acid. Why? Because it's more stable, right? And therefore, the dimethylamine is more basic. In other words, oftentimes we can compare the basicity of several compounds by looking at the pKa of their conjugate acids. As the pKa increases of the conjugate acid, the basicity increases. Right? So there's a direct correlation between basicity and the pKa of the conjugate acid. But now notice what happens with trimethylamine. Trimethylamine has a lower pKa, which means it's not as basic as dimethylamine. It's not as basic as methylamine. And as a matter of fact, it's barely more basic than ammonia. What's going on here? Well, again, solvation is the culprit, right? We saw that with the effect of acidity of alcohols. We're seeing that in the effect of basicity of amines. So the more R groups that are around, the less solvent can stabilize the charge, right? So solvation becomes important in terms of stabilizing the charge as well. And when you put R groups on, a polar solvent can't stabilize that charge as well. So we have two things going on here. We have the alkyl group certainly is donating electron density to stabilize it, but on the other hand, solvent is also playing a role in terms of stabilizing it. And you notice that trimethylamine has no hydrogen bonding characteristics, and therefore there are also fewer hydrogen bonds for hydrogen bonding to the solvents or to themselves. And therefore, this also tends to lower the stability. And you see that trend. So, things are kind of interesting and a little complicated, but you simply have to take into account all the various components. You have to take into account the effect that the groups are having, but you also have to take into account the possible solvations, the solvation effects based on stability of the products of the reaction. Now, I said that alcohols and amines are both bases, and in general, amines are much stronger bases than alcohols are, right? And we can see that if we simply look at the reaction of methylamine with hydrochloric acid to produce the methylammonium chloride. It has a pKa, so methylammonium chloride has a pKa of 10.6. If I compare that to the reaction of methanol with hydrochloric acid to give me that methyloxonium chloride, the methyloxonium chloride has a very low pKa. It's a very strong acid, and therefore, again, that is that equilibrium isn't going to be as favored as that of the methylamine, right? Remember, the higher the pKa of the conjugate acid, the more reactive, the more basic is our base. So amines are much more basic than alcohols. And here I have two compounds that are relatively similar in structure, except the only major difference is the heteroatom, right? The atom that is not a carbon, nitrogen versus oxygen. So when we think about why we see this big difference in basicity between amines and alcohols, we can certainly say that, well, oxygen's more electronegative than nitrogen is, and it cannot bear the positive charge as well as nitrogen can, right? A lot of reactivity has to deal with stability of its product. So, uh, so amines are more basic because their ammonium salts are more stable. Nitrogen can accept a positive charge better than oxygen can, and therefore it's going to be more stable than, so the ammonium salt is going to be more stable than the oxonium salt. Okay? Now, I said that amines are bases. They can also behave as an acid, but as a very weak acid. And if we look at a primary amine reacting with a base, you're going to get, when you do so, you remove a hydrogen, right? Nitrogen, the amine has a hydrogen on it. It could, in theory, be removed, and the result is what's called an amide. So nitrogen now has two pair of electrons, non-bonding electrons around it. It has a negative charge. This is called an amide. Now the pKa of amines is about 36. So it's not a very strong acid at all, right? And therefore it takes a very strong base to remove a proton from an amine. And there are not very many bases that can actually remove a proton from an amine. One such base that can is what's called an alkyl lithium reagent, which is RLI, right? This is a carbon metal bond. It's an organometallic compound, and we'll talk about them a little bit later on in more detail. But alkyl lithium reagents can do so. And I'll show you how that happens. So here I have my primary amine, and it reacts with an organolithium. So that's a carbon-lithium bond, and the electrons from that carbon-lithium bond reside more toward the carbon because the carbon's more electronegative than a metal is. What happens is I get a proton transfer. The carbon removes a proton and the electrons go to the nitrogen. The result is here now I have my amide, and then I have formed a new RH bond. This is one way of making alkanes from organolithiums, which I'll talk about how to make organolithiums in just a little bit. But alkanes have a pKa that is much greater than the pKa of amines, and therefore, we know that the equilibrium is going to lie toward the acid that has a greater pKa, and therefore we can shift that equilibrium to form the amide. But keep in mind that amide anion is a very strong base, and it's going to react with just about anything. It's going to react highly with alcohols. It can remove a proton from alcohols. It can easily remove a proton from water. It can easily remove a proton from a lot of things. And we're going to see the use of amide as an anion throughout the rest of the semester. So that gives you an idea of some of the physical properties of the substituted alkanes. The more you get to understanding the physical properties, the more you're going to appreciate and understand their reactivity.